So what we're going to do today, what I hope to have happen by the end of today is by the end of this session, you should be able to tell me about the mechanics of tendons or ligaments. You should be able to explain the relationship between movement velocity and stiffness. And so that's going to be the core of a lot of things that we do. You'll be also able to explain the relationship between movement velocity and injury. You'll define how small a bout of exercise could be in order to get full activation of the cells and really regenerate tissues like tendon, ligament, and bone. You'll be able to draw the relationship between early loading and the return to play. Does it? So essentially what that means is you'll be able to say, should we start our loading early, or should we wait until a period of inflammation has gone down before we start to load? And then you're going to be able to talk about specific types of isometrics, and you're going to be able to work your way through a couple of different kinds of isometrics. And specifically, we're going to look at an isometric that can be performed immediately after injury and has uh, the ability to accelerate return to play. And I'll take you through that as we go. All right. So the tissue that we are going to be really focused on, it's going to be this connective tissue right here that's between this muscle and this bone. And really what we would have learned when I was in taking medical school physiology is if there was anything, it would just say tendons bind muscle to bone. And it's like, oh, that's super easy. But it's actually incredibly complex because if I have a muscle, no matter how fit I am, my muscle is going to be super duper soft. Especially if I try and do the same thing with my bone is going to be hard as a rock. It's calcium phosphate. It's essentially a cement. And so what we've got is this really complex issue of taking something that's really stretchy and connecting it to something that's really stiff. And if I were to give this to a mechanical engineer and I would say, okay, I want to take this really soft material and I want to put it together with this really hard material. And then what I'm going to do is I'm going to pull on it tens of thousands of times over a lifetime. Basically, that the engineer would go into cold sweats because there's no way that they could do that, because we know that if I have a stretchy material and a stiff material, if I put them together and try and stick them together, they will always fail at the interface between the stretchy material and the stiff material. So it's an incredibly complex mechanical situation that we have, where we have a muscle that's really compliant and a bone that's really stiff. What we need is we need a tissue that's going to actually gradually change in its stiffness from the muscle to the bone, and that's really what the tendon does. And we discovered this first. Sarah Calvi, who was a student with me at the University of Michigan, she and I were doing a bunch of different experiments. And what we would do is we'd take out a muscle, and then she had a really fat cat, to be honest. But that cat had really long and very thick whiskers. And when the whiskers would fall out, we could take those whiskers and use them to paint little lines on the tendons. And what we would do is we'd paint a bunch of little lines on the on this long tendon, the TA tendon between the muscle and the bone. And so we'd have like 9 lines there. And then what we could do is we could pull it as hard as we wanted. We'd have a camera on the top. And what the camera would do is it would be able to look to see how far the lines that we had drawn on there would stretch at the muscle end of the tendon, at the bone end of the tendon, and in the middle of the tendon. And when we did that, we pulled on the muscle and we held onto the bone and we pulled on that muscle. What we got is when we looked at the 3 lines that were closest to the muscle, they were in the tendon, but they were close to the muscle. This is what was the stress. So stress is how much load there is, and strain is how far we've pulled it. So what we would do is we would pull it with, say, 2 units of nominal stress. What we would get is we get this huge stretch at the muscle end of the tendon. When we looked at the bone end of the tendon, the bone end of the tendon is this green line here. And at that same 2 units of stress, we would barely get any stretch at the bone end of the tendon. When we looked in the middle, we would get this blue line. And when we took the overall, we would get the classic kind of toe region of a tendon. And what we were discovering was that muscle end of the tendon is super stretchy. the bone end of the tendon is very stiff. And then what was happening, what the tendon is the tendon is a variable mechanical tissue. What that means is it's stretchy on one side, it's stiff on the other side. When we add to that, that's loading at a constant rate. If I were to take that same tendon and instead of loading it all at a constant rate, I would load it slowly one time. I'd let it relax, I'd let it recover, and then I'd load it quickly. What I would get is I would get different stresses and strains. So what I would see if I pulled on it slowly is it would allow me to stretch the tendon a long way at a very low stress. If I load it quickly, what happens is that tissue gets stiffer faster, and that's called viscoelasticity. So viscoelasticity is because the tissue that we're looking at here, a tendon or any kind of musculoskeletal tissue, has both an elastic component, and that's down to the proteins that are in it and all of the other structural components. And then it's got a visco component, and that means that it's got this liquid in it, and that's the water that's held within the tendon. So if I pull on it super fast, the tendon is actually a lot stiffer than when I pull on it really slowly. We all inherently know that. If we walk past a yoga studio and there's somebody with their foot behind their head, we know that they didn't get there by going as quickly as they could to that position, because we all know that that would result in something of a tear. The interesting thing is when I load it slowly, what you can see is before it starts to fail, which is at this point here, I've stretched that tendon a lot longer than when I load it quickly. When I load it fast, it's stiffer, but because it's stiffer, it actually fails at an earlier point. And so this is one of the reasons why, again, like as I said, when you walk past the yoga studio, the person has brought that foot up behind their head slowly, because if they had done it quickly, that same strain that they put on the tendon would have caused it to rupture. Okay, so when we load the tendon slowly, we're going to get a lot of stretch for not much load. But when we load it quickly, the tissue is stiffer. That means our performance is going to be better, but it's also got a greater likelihood of rupturing earlier. All right, so then it's really important that we understand what goes into the stiffness of these tendons and ligaments. So our tendons and ligaments are made up of collagen fibrils, and I've just depicted them in this little cartoon as these little triple helical ropes that come in. And these triple helical ropes that come in are going to connect together, and they're going to form these structures. So about 80%, 70 to 80% of a tendon is going to be these collagen fibrils. Those collagen fibrils are going to be linked together by these little red lines called enzymatic crosslinks. And all that means is that they're little bits that have kind of linked those collagen molecules together. Because if we just put collagen into a container and we pulled it, it would slide, those collagen fibrils would slide a little bit past each other. So when we add these little cross links, what that does is that links the two of them together as if we had put rivets into two metal sheets. And so now they're going to hold together more. The more cross links we have, the stiffer the tissue is. So the good kind of cross links are these enzymatic cross links. Those are made by the enzyme lysyl oxidase. But we can also get crosslinks from sugar, and sugar crosslinks are what we get if we have people with diabetes or if we have people who have undergone a period of inactivity. And those crosslinks, those sugar crosslinks, can also link the collagen molecules together, and that'll also make the structure stiffer. As we begin to exercise, what we do is we make more collagen fibrils within our tendons and ligaments, and when we make more collagen fibrils within our tendons and ligaments can get bigger. When we make them bigger, it doesn't inherently make them stiffer until you get more of those cross links that are in there. So the stiffness is dependent on how much collagen is there, the orientation of the collagen, which I don't show here, and the cross linking of the collagen. When I undergo a period of inactivity, what can happen is my tendons will actually get smaller because they're not getting loaded. So they'll become weaker. And then if I do that inactivity and I don't change my intake of carbohydrates or other nutrients, I can get a weak tissue that's very stiff, and those are brittle tissues, and we'll explain how that's dangerous later. All right, so our stiffness is determined by our collagen cross-linking, the content of collagen, and the orientation. I told you that the muscle end of the tendon was less stiff than the bone end of the tendon. So then, is that because there's less collagen, or is that because something else? Well, Sandra Kerwin did some beautiful experiments, and she looked at the proximal region, the muscle end of the tendon, the middle end of the tendon, and the bone end of the tendon. And what she did is she looked at these crosslinks that are making the tissue stiffer. And sure enough, as you get further towards the bone, there's more crosslinks within the tendon. The reason that that happens is when I pull on a muscle, when I pull on a tendon, sorry, when I pull on a muscle, it's going to pull at the myotendinous junction. And at myotendinous junction, the junction is actually really invaginated. It's like when I put my two hands together, interlock my fingers, now I've got this invaginated structure that's very similar to the myotendinous junction. So when my muscle is pulling, it's actually causing a little bit of sliding, and that sliding can break crosslinks at the muscle end of the tendon. And so we get fewer crosslinks at the muscle end of the tendon, and that makes the muscle end of the tendon less stiff. So then, if we want to prevent muscle injury, if you go to the popular press and you look in, say, in a magazine or in a newspaper, they're going to talk about, oh, people are stretching to prevent injury. Well, you as experts know that stretching doesn't prevent injury. This is a meta-analysis by Lawrenson. It's a little bit old. It's 10 years old now, but it hasn't changed. The data hasn't changed. If you go in and stretch and you look at the relative risk of injury, there's no change to the relative risk of injury. The thing that's going to decrease the risk of injury is heavy strength training. And heavy strength training can decrease the risk of injury by about 2/3. The reason that heavy strength training decreases muscle injuries especially is because we pull muscles when the tendon is stiffer than the muscle is strong. And so what we do with strength training is we get a little bit more sliding at the myotendinous junction. We get a slight decrease in the stiffness of the muscle end of the tendon, and we get a stronger muscle. So we have a strong muscle and a little bit less stiffness at the muscle end of the tendon. My muscle is stronger than my tendon is stiff. I'm not going to pull my muscles as well. Okay? So what we've got then is that when we lift heavy weights, we're going to get more of that activity, more of the sliding at the muscle end of the tendon. We're going to get more cross-linking being broken, and that's going to make our muscle stronger, our tendon, the muscle end, a little bit less stiff, and that is going to help us prevent injuries to our muscles. So how is this really happening? So I told you that tendons are viscoelastic. And one of the viscoelastic properties of a tendon is something that all of you know. You just don't necessarily know the words that we would call it. It's a viscoelastic property called creep or stress relaxation. What happens here is now what we're going to do is we're going to try and touch our toes. So we go ahead and we put a load on our hamstring tendons, and then we're going to hold it there. And we're going to hold it there. And as we hold it there, the tension within the tendon actually decreases in this exponential decay. And we know that. We've all experienced that because as I try and touch my toes, if I wait about 10 seconds or 30 seconds, now I can actually go a lot further. What's happened is the collagen within the tendon has begun to relax, and there's a decrease in the stiffness of that tendon. It's just a momentary decrease in stiffness. And what that has happened is we've just decreased the stiffness. And so now what we've got is we've got this really interesting component where the collagen is actually relaxed a little bit. And so when we lift a lightweight and we move really quickly, say we're jumping, say we're running, say we're doing dynamic plyometric heavy work, we're always getting this moment. We're getting the impact force of hitting the ground. we're never getting longer periods of time on the ground. So if I only do my my dynamic movements, I'm only loading my tendons with these very sharp, very fast movements. When I lift a heavy weight, what happens is it's going to take me 2 to 3 seconds to lift that to do a repetition. If I'm going to lift a weight to failure, that last repetition is going to take me a good 5 or 6 seconds. That heavy weight, I've gone through this process of stress relaxation to some degree. And that's going to be really important as we look to see how these different exercises are going to affect our muscles and our tendons. And so when we do the first one, we lift, we do that first load, we get stress relaxation. If we were loaded again from that relaxed place, and this is what you do, what commonly is done with PNF stretching, is you do a stretch, you have them push back, you have them relax a little bit, you hold it for 30 seconds or so, and then you do a second stretch where you move up. Now we go through that same process again, and you can go back and forth, and you can continue doing that. So that's the process of stress relaxation or creep. If I do a long isometric hold, and by that I mean a 30-second isometric hold, what's going to happen is the tendon will have relaxed such that the stiffness of that tendon will have decreased about 70%. So it's going to have decreased significantly. And that's going to be important as we try and understand these different loads. So if I only use lightweight, I'm going to never get this stress relaxation. If I lift heavy weights, I'm going to get a little bit of it. And that's one of the reasons why heavy weight training is really good for injury prevention. But then if I do these longer duration isometric holds, I'll actually get significantly more stress relaxation, and that could be really beneficial to these tissues that we're looking at, the tendon and the muscle. So again, people understand that when they lift heavy weights, so this is a study that we did, Dana Liss is a postdoc with me. She did this study. We had our American football team lift heavy weights for 3 weeks. They got about 7 to 9% stronger, but their rate of force development went down about 19%. Again, rate of force development is how quickly, if I pull on that tendon, how quickly does the bone move? And that's going to be decreased if I'm decreasing the stiffness of the muscle under the tendon. And this is something that most of you will be familiar with. If an athlete goes away and just does heavy lifting for a long period of time, they're going to come back, their muscle's going to be bigger. But now what's going to happen is they're going to be a step or two slower. And so that's one of the reasons why a lot of people don't like to do a lot of heavy strength training, but there's other ways that you can manipulate this to actually make it do exactly what you're trying to do, which is make this muscle stronger and not lose that rate of force development. All right. So some of what we're going to talk about today is isometric loading. And it's really important that we understand that isometric loading is this continuum. And they go from very short things that are 0.5 seconds to 3 seconds. They're really just dynamic pulls where the joint doesn't move, to 3 to 10 second isometric holds, to 30 to 60-second isometric holds. And really what we're looking at here, we're starting with maybe overcoming or yielding. So overcoming is when you start from zero and you try and push something, and the something that you're trying to push weighs more than you can move. So that's now going to become an overcoming isometric. You're trying to push, but the resistance is too much. A yielding isometric is like if I were to do a bicep curl and with 2 arms and then let go of 1 arm and try and slowly hold that in place and keep it in place. That's trying not to let it yield. And so those 2 types of loads can be done for either short periods or long periods. When we do short periods of isometric holds, they're very similar to doing dynamic holds. So they're going to give you that big uptick in stress or stiffness within the tendon. You're not going to get any stress relaxation. Over time, if you were to do those, you're going to get progressively stiffer. If you do longer isometric holds, we talked about even weight training, which is kind of a 3-second to 5-second repetition. You're going to start to see a little bit of stress relaxation. So that's going to actually help you get a little bit of a combination of now muscle strength, but a little bit on the muscle end of the tendon becoming less stiff. And if I do longer isometric holds, those are going to be good for kind of tendon health, and we'll explain why that's going to be in a minute. All right. So I explained to you that if I look at my Achilles tendon, it's going to be stiffer at the bone end than at the muscle end. And then the Achilles tendon is really good, and we're really good at preventing Achilles tendon problems, especially muscle pulls associated with the calf. Because if I've got an Achilles tendon, I've got this super long tendon. So if I'm going to do some heavy strength training and I'm going to go in and do what I'm going to get is I'm going to get a really big difference between the proximal end of the tendon stiffness and the distal end of the tendon stiffness. One of the questions that's going to be coming up on in the thigh conference up ahead is why are there so many hamstring injuries? And there's lots of different reasons, but one of the reasons is that the biology, the physiology, the anatomy of the hamstring is problematic. The tendon here for the Achilles, nice muscle. Way down here is the bone. I can have graded mechanics in that tendon. When I look at my hamstring tendon is actually an aponeurosis here and here. And what we get is we get these fibers that go from one of these tendons directly into another. I don't have a muscle end of the tendon here. There is a bone end of the tendon. There's a free tendon at the bottom. That's not usually where the problem is. There's a free tendon at the top. That's not usually where the problem is. The problem is usually at these interfaces here or here. And the reason for that is we don't have that long interface where we get the muscle end of the tendon can become compliant and the bone end of the tendon is going to be stiff. You need to have stiffness throughout most of this tendon. I can't get that graded mechanics. And so it's really hard for me and for everybody to keep the hamstring muscle from tearing. A lot of people don't really understand it. So I've come up with a very basic, and you can't see it super well because my stiff tendon is black and I'm a bit in the dark here, but you can see that I've got two identical stretchy bands that are red. I've got a stiff tendon, the black one, and I've got a compliant tendon. And so if I just take these and I hold them, the first thing that you should notice is the resting length of the muscle. The red part is the muscle. The black or the yellow is the tendon. What you can see is the muscle that's attached to the stiffer tendon is actually longer at rest. I'm going to take a step because no matter what we're going to do here with a hamstring, you have to take a step. So now what I'm going to do is the top one, remember, is the one that has the stiff tendon. If I take that step, look at the difference in how long the muscles are. The muscle for the stiff tendon is almost twice as long as the muscle for the compliant tendon. That's why we say that we get muscle pulls when the tendon is stiffer than the muscle is strong, because the tendon stiffness is going to determine how long the muscle has to be, because the muscle and the tendon together have to stretch the distance necessary to take that step. No matter what that step is, if you have a stiffer tendon, your muscle to take that same exact step has to stretch further. And when we stretch a muscle while it's trying to contract and produce force, that's those eccentric contractions which cause the most amount of damage. Okay, so that's again a little bit why we've got these hamstring injuries, and a little bit about why the stiffness of the tendon is actually going to determine whether you're going to get a muscle pull or not. So if we do everything to try and decrease muscle pulls, there is the chance that the tendon becomes a little bit the weak spot in this equation. So it has to be a combination of heavy moves and quick moves. Normally, most athletes are going to get enough quick loading on field or when they practice or when they play. And so what we're doing in the gym, if I've got a European football player, American football player, a basketball player, they're getting tons of plyometric load in their sport. In the gym, I'm going to do heavy, slow moves. If I've got a swimmer, a rower, or a cyclist who doesn't have any plyometric load in their practice, I might have to add a little bit of that in to increase the stiffness to give me better performance. All right. So again, Tendons connect muscle to bone. They're a variable mechanical tissue. The primary protein is collagen. That's the backbone. The stiffness is going to be how much collagen do we have and how much cross-linking do we have there. The water in your tendons and ligaments mean that when I load them faster, they get stiffer intrinsically. If I load it slower, it's going to not be as stiff. The speed of loading also is going to determine whether the tendon gets progressively stiffer over time, because if I only do really fast loading, my tendon is going to get progressively stiffer because what I'm going to end up doing is getting more crosslinks. If I load heavy and slow, I'm going to break crosslinks, and that means the muscle in the tendon is going to get a little bit less stiff over time. And I told you that if a muscle gets stiffer the tendon gets stiffer than a muscle is strong, that's when you get muscle injuries. All right. So the next question is, this is a little bit of background. Now what we want to do is we want to understand how to exercise tendons. Same as muscle, right? Actually, no. So we have this really cool model where we actually take, I told you that we're an hour and a half from the Sierra Mountains here. Some of the best skiing in the United States is up in Tahoe. When those individuals who go up there from the Bay Area go down and actually rupture their ACL, they'll come to us at UC Davis to get it replaced. And what we do is we take the remnant, we isolate the cells there, and we can make these little human engineered ligaments. So that's a ligament there that's now in an exercising machine. So what I can do is I can actually determine what's the best exercise for a tendon or a ligament. And really what it is if I exercise a tendon, and if I keep exercising it for an hour, 2 hours, 3 hours, after 10 minutes, I only show you 15 here because this is one of the beautiful first experiments we ran, but you can see that the signal, and that's what we're showing you here, the signal to get more collagen in a stiffer tendon actually peaks within 10 minutes. And then no matter how much more exercise you do, the signal goes away. I tell people it's a lot like my 17-year-old daughter. She's only going to listen to me for a very short period of time, about 10 minutes. And then the important thing, the next important thing to understand is how long does it take before she's going to listen to me, before I can get the cells to respond again. And my student at the time, Jennifer Paxton, who's now an associate professor at the University of Edinburgh, what she did is she stretched for 10 minutes and you got this really nice response. Then she waited for, say, 2 hours and did another 10-minute stretch. And what you can see is the 10-minute stretch done 2 hours after the first one, you actually got 40% less signal. It took fully 6 to 8 hours before you got the full signal back. And then what Jennifer did is she compared continuous loading 24 hours a day, because we have a little tissue. We can put it into an incubator with a machine that stretches it for 24 hours a day. Or we did 10 minutes of intermittent stretch, followed by 6 hours of rest, followed by another 10 minutes. And we did that 4 times. So we did 40 minutes of loading in the intermittent group, or we did 24 hours of loading in continuous group. And what you can see is it doesn't pay to load continuously. What you want to do is you want to get these 4 sessions or even 2 sessions in a day where you actually got more collagen with the continuous load, but you got twice as much collagen if you did it intermittently, 10 minutes, 6 hours of rest, 10 minutes of stretch. So our connective tissues, just like your bones, for if you didn't already know it, respond to very short periods of activity. Within 10 minutes, they've got the signal that they need in order to adapt. Everything that you do after that 10 minutes is good for your heart and your skeletal muscle. It's actually going to cause progressive fatigue and potentially damage to your connective tissues. So if you want to do the minimal amount of loading to optimally activate your tendons and ligaments, you do about 6 to 10 minutes. Doesn't matter what type of load. Ken Tam is a current PhD student. He did a really cool experiment where he either did isometric loading for those 10 minutes or he did dynamic loading. Same exact time under tension, same exact basically work. But what he found is that the strength of the tendon went up with the isometric loading and the collagen content went up with the isometric, but not with the dynamic. So what we're seeing is the isometric loading, especially on tendons, actually is really beneficial. And so this was 4 times 30 seconds with 2 minutes of rest versus that dynamic, which was continuously loading as if you're running. Again, it's a small little thing. How much does it really have to do with humans? Well, I've been showing you all the pictures of these great scientists. This one's Natalie Gilmore, who's in this. And then there's this dude. This dude doesn't look like a scientist. You're right. He's not. He's a professional rock climber and a YouTube video guy. So basically, he's an influencer on YouTube. And so what he is, he's a rock climber. He basically took one of our papers that said 10 minutes of activity and do it maybe twice a day to optimally load tendons. And he created a rock climbing strength protocol for making your grip better. And it was 10 minutes, and he did it twice a day, and he posted his results, and he got 1.25 million people to view his YouTube video. Because all of these climbers viewed it, a climbing app called Crimped put the workout, Emil's no-hang workout, onto their climbing app, and we went into the climbing app and got data from individuals who either did very low intensity, so 40% of body weight, just a weak little feel tension across the tendons within your forearm, versus max hangs, put as much weight on yourself as you can and try and hold there for 5 seconds. Or they trained with both of them. And what you can see is that there's no actual difference but in the strength to weight ratio and the strength that they gained between doing low intensity, just isometric holds for low intensity, long duration holds, compared to max hangs. They were about the same. Interestingly, when you did them both together, you actually got additive effect on strength. So what this tells us, or what this suggests to us, is that when we lift a really, really heavy weight, we're getting a stimulus for our muscle to adapt, to get bigger and stronger. We're getting a stimulus from our brain on which muscles to activate. But the other component of strength is actually force transfer, the ability to move that force from the muscle to the bones to allow us to move or to allow us to do our activities. And doing these low intensity, long duration isometric holds is just as good at increasing strength in rock climbers as you could get from lifting as much weight as you possibly could. And so what this tells us is that it could be something unique about rock climbing, very long tendons, but we also think it works in other tendons of the body, like the hamstring tendons, like the quad tendons, and we know it works for the patellar tendon as well. All right, so when we load tendons and ligaments, they rapidly adapt. When we load them, they actually respond within 10 minutes. And then it takes 6 to 8 hours before they're able to respond to another stimulus. So doing 10 minutes of rest and then say 10 minutes of activity, 8 hours of rest, and then doing your training, now you've gotten two loads on those tendons and ligaments. That's going to give you better tendon and ligament stiffness and strength. The amount of time under tension delivered using isometric loads is actually better for the tendon than when we do dynamic loads. And it increases our strength equally to very heavy work. And then when we do them both together, which is what we would suggest is one of the best things that athletes can do. They do a lot of heavy work, a lot of plyometric work on the field, and then they do these low intensity isometric works in the gym. That's going to actually increase their strength and increase their robustness even more. But no matter what we do, we're going to get these. This right here is a tendon injury. So you can see this is a rugby player, a big fella. You can see that, of course, you guys all know that there's the severity, how you're going to classify them. This is a 3, and people were kind of curious here. It's a 3B or 3C, and it's a 3BC because it does have myotendinous, but it also has the intratendinous, because you can see the tendon that goes into the hamstring, and you can see that what we've done is basically torn the muscle off the tendon. Okay, so when we have a tendon injury, what we get a process based again on the fact that the tendon is viscoelastic. We get this area that's been injured, and it doesn't matter how small it is or how big it is. We all have these little bits of tendon that are injured, and the tendon that's injured actually doesn't get loaded. What we do is we stress shield it, so the stress goes around that tendon, and the only way to really get load through this is to make the strong part of the tendon weaker. And you guys already know how to make the strong part of the tendon weaker. If I pull on it and I hold it, the strong part of the tendon will get exponentially weaker. Now this little scarred area will be stiffer than the strong part, and it'll get a uniaxial load. That's the idea. We want to load it. But what do we do in reality is we don't load it. And when we don't put load through a tendon, that's actually going to cause a scar. This is work from Hayashi in Japan, where all they did is they took rabbits, they put a wire between the patella and the tibial plateau, they unloaded the patellar tendon, and within 3 weeks or 6 weeks, they had a huge number of cells. They decreased fibril diameter, they decreased the orientation of the collagen, basically all the things that we define as a scar. But what do we do when somebody gets an injury? We stick them into a boot. What is a boot? A boot is a mechanical stress shielder. And so what happens if I model this in a rat for 3 days, I just put a little tube on their foot. Well, within 3 days, they lost 10% of their muscle mass. Within 3 days, they lost 20% of the collagen within the tendon. And the tendon went from looking like this on second harmonic generated images to looking like this, looking like a scar. So I can create a scar in a perfectly healthy tendon if I immobilize. So after an injury, the last thing in the world I want to do is immobilize. What I want to do is I want to get movement in there. What happens if we do inactivity? Well, the best example of this we think is the NFL. So American football, this is normal Achilles tendon ruptures in a 5-year period here between 97 and 2002. They get about 1 per month. What happened in this special year in 2011 is there was a lockout. The owners locked the doors and they didn't let the players practice. So they were locked out from about March until August. And then what happened is they signed a contract and all of the players suddenly went in and started training immediately. And within the first month, they had 11 or 12 Achilles tendon ruptures. Because remember, you got less collagen, but they're all sitting around. They're still eating more sugar crosslinks. That's a brittle tissue. Now I'm going to go load that brittle tissue. Bang, I'm going to get injured. So if we do have a small injury to our tendon or a big injury to our tendon, when should we load? Well, this is work out of Michael Kerr's group, best group in the world for doing musculoskeletal connective tissue, rehabilitation. Michael is an outstanding sports medicine doctor. He looked at patient recovery when he started loading 2 days after injury, that's the green line, or 9 days after injury, that's the dotted line. A 25% increase in days to recovery. So this is 50% recovery rate is 50% of the people are back to doing their training. And you can see that it's 25%. So you're going from about an average of 60 days to an average of 90 days. Okay, so that means that if I just wait a week, I'm waiting a month. It's going to take me a month to get back, a month longer to get back. So that's something to remember. You want to load right away. But how do you load an injury right away? Well, again, here, when we look at some of these isometrics, what we're doing is we're looking to improve muscle morphology and tendon with these long isometrics. What is the thing that we talked about is causing injury? That sharp plyometric or sharp dynamic movement, which causes a lot of stiffness in the tendon. But if I move slowly, I should be able to decrease that. And the best way to move slowly is isometric work. So if we isometrically load a patellar tendon injury, this is work from Danielle Steffen, who's a PhD student in my lab. What she found is that when she did the exact same time under tension, isometric versus dynamic, you can see that the tendon markers went up when she did isometric, and the cartilage markers went down. And so what that tells us is that when we load isometrically, we're getting a really healthy load for the tendon. We're getting a really healthy load for the muscle. When people do this across big groups, this is a group out of Wageningen in Holland, and they did a simple thing, which is they did an intervention group. This is their vis-a-vis or return to play is another way to do it. So the higher this is, the better. What you can see is they took this group, which was the eccentric group, the control group, versus the red line was they did the first 4 to 6 weeks were isometric training only on patellar tendinopathy or jumper's knee. And what they found is that by incorporating that patellar tendon very early isometric loading, they were able to get return to play back significantly better and significantly sooner. All right, so how do we load in that injury that I showed you? That you tore a muscle right off a tendon. What we're trying to do is we're trying to minimize that really quick rise in the stress in the tendon. So what we're doing is we're minimizing jerk. And so minimizing jerk. So jerk is not just our new president. It's that what it is a physical property. So position is where I am. My rate of change of position is my velocity. My rate of change of acceleration, or my rate of change of velocity is my acceleration. My rate of change of acceleration is my jerk. We know that jerk is damaging because tennis elbow, I'm hitting a tennis ball, my arm is swinging one way, the tennis ball is going another way, I get jerk. Golfer's elbow, I'm swinging, I'm hitting a ball, going through, I get jerk at my inner tendons of my inner arm. All of these things are telling me that this jerk is going to be the key component for injury. So the way that we minimize jerk is we put load on slowly. So we ramp into the load, we hold the load, and when we ramp off the load. So these are called low jerk isometrics. And so we take our individual, this is him here, you can see that he had his legs straight out in front of him, and this guy right here jumped on his back, and that's what caused that tendon rupture. So what do? Well, they surgically repaired it, and then we got into a big argument with the surgeon. The surgeon wanted to wait 5 weeks. We wanted to go the next day. We wanted to start loading. We came to an agreement. 9 days post-operatively, we started loading. We started loading at a long muscle length, and basically we just did 4 by 30 seconds of isometrics, 2 minutes of rest, repeated it twice a day. And basically what we did is we had him lengthen the leg to the point where, oh yeah, that's tight. Now that's where I'm going to start my contraction. I'm going to do a low jerk isometric. So I'm going to ramp into the force over 3 seconds. Now I'm going to hold that for 30 seconds. Now I'm going to let it off for 3 seconds, 3 to 5 seconds. As he can do that more and more, he can straighten his leg more. Now what he can do is he can continue to load from that long position. Once it's all the way to full range of motion, now we can start isotonic loading and progressing him normally through his return to play routine. The athlete also we had him take leucine-rich protein. That's going to be good for the muscle. 15 grams of hydrolyzed collagen and vitamin C. That's going to be good for the connective tissues in there. And basically what we were able to do with this program is get him back to full international rugby in 11 weeks. So the fastest they'd ever done it before was 16 weeks. Basically, the idea was that he was not going, and this is the individual here, he's told us that that he's happy for us to use his image. Basically, this is him at 11 weeks. By about 6 weeks, he had returned to full hamstring strength. 6 to 8 weeks, he had returned to full hamstring strength, back to full rugby. And his first game back, he was intended to play like 20 minutes, but the player who played his position got injured, and so he had to go in for 40 minutes, and this is actually him scoring a try on that first return to play. Okay, so basically what we're doing is we're using these slow low jerk isometrics that are going to allow us to develop force without any of the damaging component of the load. The damaging component of the load is the jerk. So by minimizing that jerk by a 3-second ramp up, holding it, and for your elite athletes, we're going to go with 0 pain. For a max of 2 for most of our individuals who have a much lower pain threshold than our elite athletes, we're going to hold that for 30 seconds. We're going to release that. We're going to rest 2 minutes. We're going to continue to do that. We'll do about 4 repetitions because that'll take that 8 minutes. And that 8 minutes is all we're looking for to get maximal effective dose of load. So we're going to load those musculoskeletal injuries as soon as possible. We've got lots of different examples of this now. We've got an Olympic athlete who had quad tendon surgery. We loaded him the next day after his surgery. His return to play was extraordinarily quickly, got back in time for an Olympic Games where they thought he was going to miss it. And again, it's not just getting back. He won 2 gold medals. We can do loading at long joint angles. We always try and kind of protect it early on. That's the tradition. But what we do is we go through, we had an individual with a pec strain. He would take his arm back until he felt tension across there, until he felt, oh yeah, that's about as far as I can go. That's where we're going to start the isometric. When he can go back to full range of motion, that's when we can move into his isotonic work and we can get him going through his progression in his return to play. We supplement with leucine-rich protein, about 30 grams of it. So that's usually whey protein. And then we add 15 grams of hydrolyzed collagen and vitamin C. And you can do that either before or immediately after training, because again, this is a muscle tendon unit. So that's going to have better blood flow than if we were just delivering it to the tendon alone. All right. Okay, so take-home messages for everybody here. In the gym, we use weight to determine the velocity of the movement. So if I lift a heavy weight, move is going to be slow. If I lift the lightweight, move is going to be fast. So when I'm programming athletes in a gym, I'm going to have them lift a heavy weight if I want them to move slowly and I want to get a positive effect on the tendon. And I'm going to have them move quickly if I want to have them increase the stiffness of that tendon over time. So as I go in for more high performance, I'm going to go with shorter, faster moves. Heavy loads mean slower movements, decrease the muscle end of the tendon stiffness. Tendon and ligament cells respond better to isometric loads than dynamic loads. Really, all that's happening is when we load quickly, the load is only going through a small part of the tendon where the strongest collagen is. When we hold an isometric, that load gets through the whole tendon, because as the strong part relaxes, the next strongest part, then the next strongest part gets brought in. They all get the signal. Okay, but combining both isometric and dynamic loads is the best way to increase strength and increase the robustness of an athlete. No matter how well we prepare our athletes, we're going to get injuries. When they do, we're going to start loading immediately. When I have personal injuries, I'm loading the same day that I injure myself, and I'm going to do it using these low jerk 3-second develop force, hold 30 seconds, release force over 3 seconds. And the loading of these injured tissues can start at long joint angles, but should be pain-free or nearly pain-free. Short bouts of loading, again, 30-second holds, 4 repetitions with 2 minutes of rest in between at least once a day. Okay, and you can supplement with some protein.